All right, so today we're diving into something I know you deal with every day, machining those intricate titanium parts
Right.
built with LPBF.
Yeah.
So we're going to explore how the unique nature of these parts
Okay.
can really kind of throw a wrench in your production process.
Interesting.
Think of this as your cheat sheet to understanding why
Yeah.
LPBF titanium
Yeah.
sometimes behaves well differently.
And to guide our deep dive today, we're
right.
going to be using a recent research paper from Virtual and Physical Prototyping
Okay.
by Ni et al.
All right.
It's titled Recent Advance in Laser Powder Bed Fusion of Ti6Al4V Alloys, Microstructure, Mechanical Properties, and Machinability.
So titanium,
Yeah.
it's the superstar in so many fields, aerospace, biomedical, even maritime.
Of course.
We all know it.
Yeah.
It's strong, biocompatible, corrosion resistant, basically a superhero metal.
Right.
But as with most superheroes, there's a catch.
There is. The catch is that titanium alloys can be incredibly difficult to machine.
Oh, really?
Yeah, and this is because they have low thermal conductivity, high chemical reactivity, and a low elastic modulus.
I see.
What that means for you is, well, traditional machining methods often lead to excessive tool wear and a lot of wasted materials.
Yeah, I see. So enter additive manufacturing.
Right.
Specifically LPBF. It's like the sidekick that comes in to save the day.
Okay.
Allowing for those intricate designs and personalized customization that are so crucial in these fields. But LPBF also brings its own set of challenges, right?
Absolutely.
Yeah.
The process involves rapid melting and solidification of the titanium powder at cooling rates that can reach 10 to 10 Kelvin per second.
That's incredible.
We're talking about extreme temperature gradients.
Okay.
Up to 10 Kelvin per meter.
Jeez, imagine the forces at play
within the material as it solidifies under those conditions.
That's mind-boggling.
It is.
It's no wonder that these extreme conditions can lead to defects in the final part.
Absolutely.
Right.
The paper highlights issues like lack of fusion, porosity, balling, and even microcracks.
Wow.
They even include micrographs that show you exactly what these imperfections look like.
Very cool.
And the paper goes deeper, exploring how these defects are influenced by those critical LPBF process parameters. We often hear about laser power, scanning speed, hatch spacing, layer thickness, and the scanning strategies themselves.
I see.
Controlling these parameters is key to minimizing those defects and getting a high-quality part.
So we've got this powerful process that can create amazing parts, but it requires a very precise touch.
It does.
It's almost like walking a tightrope.
It is.
You know that.
A very apt analogy. Yeah. And to add another layer of complexity, the rapid cooling rates inherent to LPBF create a very specific microstructure within the solidified titanium. We're talking about a mix of what's called acicular martensite and elongated prior columnar grains. Think of these grains as the building blocks of the material.
And the paper actually shows us what these structures look like under a microscope.
Yeah.
It's fascinating to see how LPBF creates these intricate details at such a small scale.
At such a small scale. What's important here is that this unique microstructure leads to anisotropy.
Anisotropy.
Yeah. In simpler terms, this means that the material's properties, its strength, hardness, even how it reacts to machining, vary depending on the direction you're looking at.
So if I'm machining a surface that's perpendicular to the build direction, I'm going to get different results compared to machining a surface that's parallel to the build direction.
That's right.
So it's almost like working with wood that has a pronounced grain pattern.
Yeah.
You can cut smoothly with the grain.
Exactly.
But trying to go against it creates resistance and tear out.
That's a great analogy.
Yeah.
And the paper actually provides data to back this up. They found significant differences in surface roughness and cutting forces when comparing machining on those two different surfaces. It really underscores why understanding this anisotropic behavior is so crucial for anyone working with LPBF titanium.
This makes me think about all those tool wear issues that are so common when machining titanium.
Right.
It's not just about the materials inherent properties, but also how those properties change based on direction.
Exactly.
It has a whole other layer of complexity.
Absolutely.
And that's why the paper goes on to explore some advanced machining techniques that can be used to overcome these challenges, specific to LPBF titanium.
Okay.
Techniques like micro-quantity lubrication, MQL, ultrasonic vibration-assisted cutting, UVAC, cryogenic machining, and high-speed machining all offer potential solutions.
They do.
Let's take UVAC as an example.
Okay.
The paper mentions that it can be particularly effective for LPBF titanium.
Right.
But how does it actually work?
Yeah.
What's happening at the cutting edge?
UVAC introduces high-frequency vibrations to the cutting tool.
Right.
Imagine those vibrations superimposed onto the tool's normal cutting motion.
I see.
What this does is essentially reduce the contact area between the tool and the workpiece.
Okay.
This reduces friction and, as a result, lowers the cutting forces and heat generation.
So instead of a constant forceful engagement, the tool is kind of dancing across the material surface.
Yes, and that dance has a significant impact on the machining process.
Oh, wow.
Lower cutting forces translate to reduced tool wear, and less heat generation means better surface integrity.
Interesting.
Plus, those vibrations also disrupt chip formation, creating smaller, more manageable chips that are less likely to clog the cutting zone.
That makes sense. Smaller chips mean less chance of those chips getting wedged between the tool and the workpiece, which would increase friction and heat.
Exactly.
And the paper actually showed images comparing the chip formation and surface morphology under different machining conditions.
They did.
Those visuals really bring the point home.
They do.
They showed smoother, more continuous chips with UVAC compared to conventional machining, where the chips were larger, irregular, and more likely to cause problems.
Right.
So it's not just about brute force when it comes to LPBF titanium.
It's about finesse.
It's about finesse.
Using techniques like UVAC that work with the material's unique properties instead of fighting against them.
Instead of fighting against them.
Precisely.
And the paper goes on to highlight how these advanced techniques can be tailored to address specific challenges posed by the microstructure of LPBF titanium.
Okay.
Okay, now I'm really intrigued. What other examples did they give?
Well, they talked about micro-quantity lubrication, or MQL.
Right.
This technique involves applying a very small amount of lubricant, think a fine mist, directly to the cutting zone. This minimizes the amount of lubricant used while still providing those crucial benefits of reduced friction and cooling.
That sounds like a win-win.
It is.
Especially when you consider the environmental impact of traditional flood coolant methods. Less waste, less mess. And still achieving the desired results.
Exactly. And the paper highlighted how MQL can be particularly effective in combination with other techniques like UVAC. By combining these approaches, you can really optimize the machining process for LPBF titanium.
It's all about finding the right combination of tools and techniques. Recognizing that LPBF titanium demands a more nuanced approach.
It does.
Compared to traditional titanium alloys.
Absolutely. They also touched on cryogenic machining.
Cryogenic machining.
Which involves cooling the cutting zone with liquid nitrogen.
Oh, wow.
Now, this might sound a bit extreme.
That sounds pretty high-tech.
What
are the benefits of going to such extremes?
Well, the extreme cold strengthens both the cutting tool and the workpiece. This means reduced tool wear and improved surface integrity. Plus, it helps minimize those pesky chemical reactions that can occur between the tool and the workpiece at high temperature, reducing tool wear and improving the quality of the cut.
So it's not just about slowing things down.
No.
It's about changing the fundamental behavior of the material.
It is.
At a molecular level.
At a molecular level.
It sounds like cryogenic machining is a powerful tool.
It is.
But probably not something you just set up in your garage.
You're right. It does require specialized equipment and a certain level of expertise. But for those working with LPBF titanium parts that demand the highest levels of precision and surface quality, cryogenic machining is definitely worth exploring.
Well, it sounds like the future of LPBF titanium machining is full of exciting possibilities.
It certainly is. Yeah. The paper does a great job of pointing us in the right direction for further research and development. Yeah. This knowledge of anisotropy and these advanced machining techniques open up a world of opportunities to optimize the production process for LPBF titanium parts.
So for our listeners out there who are wrestling with these challenges every day, what's the key takeaway from all of this?
Machining LPBF titanium is a balancing act. Okay. You need to approach it with an awareness of the unique anisotropic properties of the material, those elongated grains created during the LPBF process mean that machining strategies that work for traditional titanium alloys may not be effective or could even be detrimental.
So it's not just about selecting the right tool or setting the right parameters on the machine. It's about understanding how those choices interact with the specific microstructure of the LPBF titanium part you're working on.
Precisely. And this leads to a final thought-provoking question for our listeners. How can we use this knowledge of anisotropy to our advantage? For example, could we strategically orient parts during the build process to improve machinability on critical surfaces? Or could we develop customized tool paths that take into account the directional variations in material properties to optimize both surface quality and tool life?
Those are some great questions to consider.
They are.
And I bet our listeners have a lot of insights and experiences they could share.
I think so.
We encourage you to reach out and tell us about the challenges and triumphs you face when working with LPBF titanium parts.
Absolutely.
After all, it's through collaboration and shared knowledge that will continue to push the boundaries of what's possible with this incredible technology.
Yeah.
So until next time, happy machining.
So we were talking about MQL and how it minimizes the use of lubricants.
Right, less waste, right?
Yeah.
So what about cryogenic machining?
Oh, yeah, cryogenic machining.
That's the one with the liquid nitrogen, right?
Yeah, exactly.
I mean, that sounds kind of extreme.
It does sound extreme, but it can be really effective.
Okay, so what are the benefits?
Well, with cryogenic machining, you're basically using the extreme cold to strengthen both the cutting tool and the workpiece. Oh. So you get reduced tool wear. You get improved surface integrity, and it helps minimize those chemical reactions that can occur at high temperatures.
So basically changing the behavior of the material at a molecular level.
Molecular level, yeah.
So I guess cryogenic machining is not something you could just set up in your garage.
Well, you're right. It does require specialized equipment and a certain level of expertise. But for those really high precision parts where surface quality is critical, it's worth looking into.
Okay, so it sounds like we've got all these different approaches. And each one has its own advantages depending on the specific part and the desired outcome.
Absolutely. It's all about finding the right tool for the job.
So I guess the key takeaway for our listeners is that machining LPBF titanium, it's not a one-size-fits-all kind of thing?
It's not a one-size-fits-all approach, no.
You really need to understand the unique properties of the material.
Yeah, and the paper does a great job of highlighting that those elongated grains from the LPBF process mean that your machining strategy has to adapt. What works for traditional titanium might not work here.
So I guess the big question is, where do we go from here?
Well, that's a great question.
What are some of the things that researchers are exploring?
Well, one thing they're looking at is how to use this knowledge of anisotropy to our advantage.
Okay, so how could we actually do that?
Well, for example, could we orient parts differently during the build process.
Interesting.
To improve machinability on those critical surfaces.
I see.
Or what about customized tool paths that actually take into account the directional variations in the material?
To get the best results.
To get the best possible results, right?
So it sounds like there's a lot of potential here.
There is.
For innovation and improvement.
Absolutely.
And we're really just at the beginning.
I think so.
Of exploring what's possible.
Yeah.
Well, this has been a fascinating deep dive.
It has.
Into the world of LPBF titanium machining.
It really has.
I've learned a lot.
I'm glad.
And I'm sure our listeners have too.
Me too.
So thanks for joining us today.
It's been a pleasure.
And for all of you out there in the manufacturing world, keep pushing those boundaries.
Yeah.
Keep innovating.
Keep innovating.
And until next time.
Until next time.
Happy machining.